For this question, again, like the previous question, um, I'm not going to put any numbers. Instead, I'm just going to use variables because this type of question happens a lot. And I think once you learn how to solve it with just the variables, then you can just replace the variables themselves with numbers. So what we have here is a projectile that's launched from some position, and it's on an angle with respect to the horizontal. So that angle here is theta. The launch speed is v, so that's the initial velocity. And that technically happens right here. The projectile itself follows a parabolic shape. So the only time when the velocity is going in this direction is right at the beginning. At every other time, it's sort of becoming less steep. So therefore, that vector doesn't apply for the entire journey. In fact, it only applies for the fraction of a second right after it's initially launched. You'll also notice that between where the projectile begins and where it ends, I'm assuming it ends here, the ground is irregular, but for the purposes of this problem, the ground could be flat, or it could be a giant hill here, or more of a deep valley. It doesn't matter. All we have to realize is that the change in vertical displacement is zero. So the projectile starts and ends on the same level. So as soon as you realize that those two criteria are met, that the projectile starts and ends on the same level, and that it makes an angle with the horizontal, then you can apply this type of strategy to any projectile problem that looks like this. Okay, so the first thing we're going to do is we're going to break this into components. So we're going to look at what's happening in the x direction and what's happening in the y direction. So in the x-axis, our givens are, well, we have an initial velocity vector that is the cosine of theta times the velocity on the hypotenuse here. So Vix is equal to V cos theta, because this side is adjacent to this angle, and if we rearrange the cos, then we get this side right here. So this is Vix. I'll just show you quickly how to get that. Cos of theta is equal to adjacent over hypotenuse. In this case, adjacent is Vix. Hypotenuse is V. And then if we're looking for Vix, we get V cos theta. So that's how I get that. So this is some units. Again, this could be meters per second, kilometers per hour, kilometers per second, something like that. And the direction is for V is right theta up, so that's this, but the direction for Vix is just to the right. So this is to the right. And what else do we know? Well, this is a projectile, so that there's no force happening in the x direction, so therefore acceleration is equal to 0 in the x direction. And in this case, we're looking for the range, so delta dx. Now the key, like any projectile problem, is to solve for t, because t is the key that connects the x-axis with the y-axis information. So for the y-axis, so that's the x-axis. For the y-axis, let's just erase this. We have VIY is equal to V sine theta, and the direction in this case is units up. Sorry, I erased this. This is units to the right. we have an acceleration due to gravity, which is negative 9.8 meters per second squared up. Now I just realized that because we're using meters per second squared, we actually know what our units are. So we should realize that our units have to be converted to meters per second. So if the problem does give it in some other units, we'll have to convert that to meters per second if we want to use negative 9.8 meters per second squared as our acceleration down. Okay, so what else do we know? We know that delta dy is 0, and we can solve for t. We have enough information to solve for t in this case, and then we can use that to solve for delta dx in the x-axis, because these are the same. So let's go ahead and pick a kinematic equation that has all of this. And so what we get to choose is delta dy is equal to v iy times delta t plus a half a delta t squared. And that's the y, that's the acceleration in the y direction. So this is 0. This is v sine theta dot delta t plus we get, where I'm just going to replace this with g, so I'll call that g. So this is g over 2 delta t squared. Now this is, I'm going to factor out the delta t's. Now what this tells me is that one of the answers to this relationship is delta t is equal to 0. Because if this is 0, then 0 times whatever this is becomes 0 on the right side equals the left side. And that makes sense because this is a parabola, and essentially what we've asked this equation to solve for us is where does the parabola intersect this line? And one of the places it does intersect is right at the beginning of its journey. We're interested in the part where it intersects this part, which is non-zero time. So that means we have to solve for delta t here. So what does that mean mathematically? Well, that means that we are going to find what delta t has to be in order for this whole chunk to be 0. Because it doesn't matter what the delta t is. If this is 0, then 0 times some non-zero number will get us 0. So what I'm going to do is set this equal to 0. And I'm going to say delta t, 0 is equal to v sine theta plus g over 2 times delta t. And now we're just going to solve for delta t. So I'm just going to move this to the next page. Just make sure that's the right equation. Yep. So I'm going to bring this over to the left. And then I'm going to multiply both sides by 2 to get rid of the 2 on the denominator. And I'm going to divide both sides by g. Now remember, g itself is negative, so that will cancel out with that negative and give us a positive time. So the next thing we do is we're going to sub this into, so we'll call that equation 1. We're going to sub equation 1 into the information in the x-axis. So we'll use the equation delta dx is equal to v ix times delta t. And we can use this because acceleration is equal to 0. So delta t is equal to this right here. And Vix, if you recall, is v cos theta. So if we go back, you can see that Vix is v cos theta. So it's equal to v cos theta times negative 2v sine theta over g. And if we simplify things, we get negative 2v squared. So v times v is v squared. And then we have sine theta times cos theta over g. Now again, this would be a positive value because this is a negative value. We just replaced the whole negative 9.8 with little g. So if we had a question with numbers, so if this was 10 meters per second at an angle of 20, we would have everything here. We would replace that with 10 squared sine 20 cos 20 over negative 9.8, and we would get a value here. So therefore, the range is negative 2v squared sine theta cos theta over g. And this equation may look slightly familiar because if you use some trig identities, you can actually condense this formula so that it looks like this. And this time I will take away the negative. We'll just make g a positive value. So we get v squared sine 2 theta over g. And that's called the range equation.